Swayam Prabha. Digital India. Educated India.
Okay, so we are in our 8th lecture, and today we shall be discussing decision modeling, the special cases in linear programming. We shall have a series of 3 lectures in special cases. So today is the first one, and in this particular class, we shall be focusing on degeneracy. Now, we have already seen linear programming problem and how to solve those problems graphically, as well as with the help of the simplex algorithm. We shall be discussing out of these linear programming problems 4 different cases. What are they? First one is degeneracy. The second one is alternate optimal solution. Third one is infeasible solution space, and the fourth one is the unbounded solution space. Essentially, what we exactly discuss is what are these special cases and when do they occur, what is the definition of these special cases, and specifically how to understand them when solving the problem graphically or by the simplex algorithm. Apart from that, we should also understand that when these are observed, what are their impacts on the solution that we have obtained in the simplex problem, I mean linear programming problem, and what exactly we should do under these situations. Now, degeneracy occurs when there is some values are zeros in the basis. You see, what is the solution methodology in linear programming? We have a problem, and then we have a lot of inequality constraints. We turn those inequality constraints to equality constraints by adding some more variables like slack variables, artificial variables, and surplus variables, as the case may be. And then we get more number of variables, then there are equations. We cannot solve all of them. We can only solve the, supposing there are n number of equations and m number of variables, we can only solve n, and we cannot solve all of m, which is higher than n. The remaining m minus n variables we actually put to zeros. And those variables which we are putting to zero values, they are called the non-basic variables. And those variables which are not put to zero values, which are actually solved from the equations after putting the non-basic variables to zeros, they have some values, and non-zero values, or even zero could be there as well, greater than equal to zero values. Those are the basic variables. Degeneracy occurs when even some of the variables which are in the basis, they also become zero. So that is called degeneracy. The second case, which we shall discuss tomorrow in our next class, that is alternate optimal solution. So when the profit line is parallel to one of the bounding constant lines, then what we might have see that these entire bounding constant line also becomes optimal. So in simplex cannot find out in between points because it only works with the corner points. So essentially there will be two basic feasible solutions, or even more than two could be returned as alternate optimal solutions. And those two basic feasible solution, not only are they optimal if they are joined by a straight line, which is the bounding constraint line, then all point on that particular line, they also become optimal. So this is about the alternate optimal solution. The third case we shall take up is the infeasible solution space. Here the constraints are such that the solution space is not possible to have, right? So constraints will not allow a solution space to form. So that means there is no solution possible to the problem at hand. In a sense, we say that the problem is infeasible and solution is not possible. That means infeasible solution space. Now, how to understand that graphically? That is, we shall see that there is no solution space, but how to understand it while solving the problem using the simplex algorithm. The fourth case is the unbounded solution space. Here, yes, the solution space is available, but it is not bounded. For a minimization problem, this may not be a problem because we always know that it is always bounded by the two axes on the lower side, x1 axis and the x2 axis, and 0, 0 is a viable point until unless it is cut off by some constant line. So even if it is cut off by a constant, the lower bound will be always available. So for minimization problem, usually the unbounded solution space is not a problem. But for a maximization problem, it is definitely going to be a major problem because in that case, the optimal solution may be infinity. So these are the four different cases that we shall discuss, and today we shall discuss what is known as degeneracy that occurs when there is a zero value in the basis. So here is a linear programming problem that we have taken, and in that linear programming problem there are two variables. Maximize z equal to 3x1 plus 9x2 subject to x1 plus 4x2 less than equal to 8, x1 plus 2x2 less than equal to 4, and x1 and x2 both greater than equal to 0. So the augmented problem would become we have to add two slack variables for the two different constants, and say x3 and x4. So x1 plus 4x2 plus x3 equal to 8, x1 plus 2x2 plus x4 equal to 4. And obviously maximize z equal to 3x1 plus 9x2 plus 0x3 plus 0x4, and all the four variables are greater than equal to 0. So let us try to see this, that because there are four unknowns and two equations, so 4C2, that means there will be 6 basic solutions, right? Because there will be 6 basic feasible points that we are going to get. Out of those, 6 basic solutions, out of the 6 basic solutions, not all will be feasible, only some of them will be feasible. So here is the graphical solution to the problem. This line is x1 plus 2x2 equal to, and x1 equal to 4x2 equal to 8. So where are the 6 basic solutions? You see, we could see only 3 basic feasible solution. All right, and there is a fourth point, C. So how many points are we seeing? O, A, B, and C. But we seen that because there are 6 basic solutions, that means we should get 6 different corner points. Some will be feasible, some will not be feasible. All right, so here O, A, B are feasible corner points, and C is the infeasible corner point. So it's a basic solution, but it's not a basic feasible solution. Now finding the graphically the solution is not a big deal. We have to evaluate the points O, A and B. O, the value of Z is 0. A, the value of Z is 18. And B, the value of Z is 12. So 18 is the highest, and therefore that is the optimal solution. And solution therefore is x1 equal to 0 and x2 equal to 2. So easy to find out graphically the solution. But look here, this is basically an degenerate point. Now, why it is a degenerate point? See what has happened. The two constant lines, that is AB and AC, and the axis, all three have merged at a point A. What is the significance of that? Even the basic, very important question is where are the 6 basic solutions? That is also an important question. All right. So we see there are actually 3 points merged in the optimal point A. What are these? You see here we have now shown basically if you go back to the augmented problem. So this is our augmented problem. You can see that there are 2 unknowns and there are 2 slack variables. So there are 4 different unknowns, and in this line that x1 plus 4x2 equal to 8 can also be said as x3 equal to 0. And this line that is x1 plus 2x2 equal to 4 can also be said as x4 equal to 0. So two constant lines are actually x3 equal to 0 and x4 equal to 0. And obviously we have the two axis line x1 equal to 0 and x2 equal to 0. So if we plot them, this is the x2 axis, that means x1 equal to 0. This is the x1 axis, the x2 equal to 0. And this is x1 plus 4x2 plus equal to 8, so x3 equal to 0. And x1 plus 2x2 equal to 4, so x4 equal to 0. So look here, we are putting two variables to 0 at a time. So if you put x3 equal to 0 and x1 equal to 0, so suppose we call it point A1, and then x1 equal to 0 and x4 equal to 0, so we get the point A2, and x3 equal to 0 and x4 equal to 0, so point A3. See what happens that when you are solving by simplex, we have to be careful about which point are we getting. Are we getting A1 or A2 or A3? But look here, really speaking, these 3 points are merged and there is only a single point A. So you see, total the 6 basic solutions can now be seen. That is 1 point here, 1 point at B, 1 point at C, and 3 points at A. A1, A2, A3. So these are our 6 basic solutions. Out of that, 1 is infeasible and 5 are feasible solutions. So there are 5 basic feasible solutions, but we are seeing only 3, that is O and A and B, because A1, A2, A3, all of them has merged at a single point. Look, these are single points, so we can understand it because we are solving it graphically. But when you solve by simplex, it will not be possible to understand, not only by the human who is solving it manually or by the computer when it is solved by the computer. So what will happen? You can actually go from one solution to the other and to the next without any improvement in the objective function, because essentially you are at the same point. As long as the values are the same, because the point is the same, the objective function value also would be the same. So what is happening? You are iterating without any improvement in the objective function value, and you are basically cycling within the same point. And by mistake, if you are coming back to the old solution, then you can be keep cycling infinitely. Go to A1, then A2, then A3, again come back to A1, then A2 to A3, and A1, A2, A3. You are in an infinite loop of cycling. So this is cycling is a problem that is attached with degeneracy, and we shall discuss cycling a little bit more. But more than cycling, that zero value in the basis and there is no improvement in the solution. That also is a difficulty because we are taking many more steps that are not necessary, and the problem solution is not arriving even though the point is reached. So these are the various issues that are related to the concept of degeneracy. Is it all right? So this is what happens. The graphically all 3 points are optimal, and we say that there is degeneracy at the optimal point. Is it all right? Because 3 points are merged at the optimal point A, and therefore we are having this kind of situation. Now, if we solve the problem by simplex, let us see what really happens. Right? What are we trying to do? We are solving graphically this particular problem. Now we are trying to solve the same problem by simplex. So here is the simplex. Now this is the problem that x3, x4 values 8, 4. So 1 4 1 0 1 2 0 1, x3 and x4 forms the uh, unity matrix because they are the basic variables. They are in the canonical form, and these are the cj. Zj value is 0. So initially cj minus zj are 3 and 9. So x2 enters the basis. So which one should be the living variable? Look at it carefully. Which one is the bottleneck resource? X3 is the bottleneck resource or X4 is the bottleneck resource? Total value available is 8, coefficient is 4. So 8 by 4 is 2. That means 2 X2 can be made if we make use of X3 resource. But if you make use of X4 resource, 4 is available, requires is 2 per unit. So again 4 by 2, so 2 can be made. So what have we got here? We have got a tie in the living variable. So whenever we have a tie in the living variable, two resources gets exhausted at the same time. That means both are bottleneck resources. So if both are bottleneck resources, what is going to happen? In the next table, we are going to get a 0 in the next table. So that means the degeneracy will be obtained. So how to predict a degeneracy? If we find a tie in the living variable. Is it all right? So when we find a tie in the living variable, we know that two resources have got depleted at the same time, and both are bottleneck resources. Any one you choose, the other one will assume a 0 value in the next table. All right, so this is exactly what is happening. So it has happened here. So observe that there is a tie in the living variable. Both x3 and x4 are candidates because 8 by 4 equal to 2 and 4 by 2 is also equal to 2. Now which one to choose? We choose any one. In this case, let us choose x3. So if we have chosen x3, so x3 is the living variable, x2 is the entering variable. Is it okay? So therefore the next table would be now obtained. So here is the next table. This is the key row. So key row items would be divided by the intersecting element, which is 4. And therefore x2 comes into the basis, x3 goes out of the basis. So value become 8 by 4 equal to 2. This 1 becomes 1 by 4. This 4 becomes 1. This 1 becomes 1 by 4. This 0 becomes 0. This is to be easily computed. Now for next row, 4 minus 8 into 2 by 4. So we get a 0 here. 1 minus 1 into 2 by 4. So we get half here. And key column would be in unity matrix. So part of unity matrix. So it should be 0. So 1 0. And this 0 should be 0 minus 2 into 1 by 4. So minus 1 by 2. And this 1 will be 1 minus 0 into 2 by 4, so 1. All right, so this is how we got the solution, that is x4 equal to 0 and x2 equal to 2. Look here, the objective function, the optimum solution has already been obtained because already we got x1 equal to 0, x2 equal to 2 and z equal to 18, but it is not showing optimal. This is interesting. What has happened? We are now moving between those 3 points. Is it not? So this is one of the 3 points. So optimum solution is reached, but still we might go iterating. Why? Because look here, for x1 it is 3 minus 9 by 4, so it is 3 by 4. Whereas for x3, 0 minus 9 by 4, so minus 9 by 4. So 3 by 4 is still positive. That means x1 can still come into the basis. But what is happening? X1 is coming into the basis, and we have already got the optimal point x1 equal to 0 and x2 equal to 2, which we have already seen before graphically. Right, so graphically we have observed that the optimum solution is x1 equal to 0 and x2 equal to 2, and in the second table itself we have got that optimum solution. But this optimum solution is we are not accepting because x1 is now coming into the basis. All right, so this is what has happened. So this degeneracy has occurred. That means, all the 3 points A1, A2, A3 are optimal. So what exactly has happened? We have got, um, these x4 equal to 0 and x2 equal to 2. That means x1 and x3 are non-basic variable, and x1 and x3 has been put to zeros. So you see, we are really at point A1. That is, x1 is put equal to 0 and x3 equal to 0. So A1 is where we are. Right? Currently, we are at point A1 because x1 and x3 are non-basic variables and their values are 0. All right, although the optimal point has already been reached. So we know that there is degeneracy. Now, this is the second table. So which variable enters? Now x1 enters because it has a positive Cj minus Zj. Which variable leaves? X4, because after all, there is a 0 entry. So this is the bottleneck resource because there is no resources available. So x4 leaves, x1 enters. So what are the new basic variables? X1 and x2 in the next table. In the simplex third table, x1 and x2 would be our basic variables. So which variables are not in the basis then? X3 equal to 0 and x4 equal to 0. So they are in the non-basic variable. So what is really happening? We are moving from second table, which is showing point A1. We are going to x3 equal to 0 and x4 equal to 0. That means we are going to point A3 from point A1. So this is the point A3. All right. So this time, this is the key row. So key row would be divided by the intersecting element half, but 0 divided half equal to 0. And this would become 1, half divided by half. 0 divided by half, so 0. So this one is minus 1 and this one is 2. And then this 2 is 2 minus 0 into this, etc. So become 2. Because of canonical form, this is 0, 1 and 1, 0. And then this 1 by 4 becomes half and this 0 becomes minus half. And if we now compute Cj minus Zj, then we get both negative. And then we say, yes, it is the optimal point. So now we see we got A3 as the optimal point, but this table, which was actually showing A1, that was also optimal. What really has happened? X1 has come into the basis, but with a 0 value. So really speaking, it has not contributed any improvement in the profit, right? So objective function value has not changed. So note that solution represented by the third simplex table, that is x1 equal to 0, x2 equal to 2, and z equal to 18 is the optimum solution, and non-basic variables are x3 and x4. So they are put to zeros, and that is the point A3. So A3 is returned by the simplex as the optimal point, although the previous table, which was representing A1, was already optimal. So this is a degeneracy. So we know that degeneracy can be predicted if there is a tie in the leaving variable. That means next table would be tie. Next table would have a 0 in the basis. All right. And then we might do more iteration than necessary, unnecessarily. because although they are same point, but simplex is not able to identify it immediately. All right, so that is the essential idea of degeneracy. So suppose someone asks you what is degeneracy, the answer is very clear: a zero value in the basis, right? That is degeneracy. How degeneracy is observed in simplex: when there is a tie in the living variable in a table, then we know the next table is going to represent a degenerate point. All right, so this is what that note that same solution is resulted in second and the third simplex table, but they represent two different points merged into a single point. Z value does not improve from table 2 to table 3. There is also a zero in the basis of the final simplex table. So these are some of the observations. Once again, the two different points are merged into a single point. Z value does not improve from one table to the other, and final table also has a zero in the basis. All right, so this is how the degeneracy is to be evaluated. Now here are some observations on degeneracy. What are some observations? First of all, degenerate solutions arise because some values are zeros in the basis. So this is the first thing. Second thing, whenever there is a tie in the living variable, the next solution comes out to be degenerate. In case we get degeneracy, the next simplex table does not improve the objective function. So these are some direct observations that we can see on degeneracy. Now I was talking about cycling also. In case of degenerate solutions, it is possible to obtain a series of simplex W with each of them having the same objective function value that may bring us back to a W that has been considered earlier. So this is called cycling. So we have seen that there are three different points. Now assume there are four different points that have been merged at a given table. So how many points are merged? 4C2. What is 4C2? 4 into 3 by 2 into 1. So 6 different points are merged at a particular point. So 6 different points. So it is possible that you go from table 1 to table 2 to table 3 to table 4 and then come back to table 1 and keep doing those operations, and we can never come out of this kind of thing. But will it be the case all the time? You see, what is happening that if you are coming from table 4 to table 1, probably you are breaking the tie arbitrarily. But suppose if you break the tie by following a simple rule, that is, one such rule is the Bland's rule. The Bland's rule says that at any point of time, if there is a tie, take the leftmost variable to leave the basis. Is it all right? So what is leftmost variable basically? So, this is a table. So this is a simplex table. So if you look at these variables x1, x2, x3, x4, then x1 is the leftmost, x2 is the next left, x3 is the next left, and x4 is the next left. All right, so go back to the first table. So here is our first table. So in the first table, there is a tie in the living variable. So what are the variables? X3 and X4 both can be living. Now what with the Bland's rule is saying that X3 is towards the X4. All right, so choose X3. In other words, the Bland's rule can also be expressed as that if there is a tie in living variable, choose that variable that has a lower index. So x4 index is 4, x3 index is 3. So we see that x3 has a lower index than x4. So choose x3. So what has happened if we break the tie by following a rule such as Bland's rule? What is going to happen? All the time you are going to get the leftmost variable. So it is not possible that you choose x3, then x4, then x5. It is not possible that you come back to the because you are always choosing the leftmost variable. So you cannot get back to the same table once again. So one by one you will follow those tables, and you do not come back to the same table, and therefore the cycling can be avoided. All right, so this is the essential thing. We'll discuss more about cycling, but one such example is created by VL. So this particular problem has been created, so that uh, we have what is known as cycling uh, to be created all the time. So this problem is like this, that minima is z equal to minus 3 by 4 x4 plus 20 x5 minus half x6 plus 6 x7, subject to x1 plus 1 by 4 x4 minus 8 x5 minus x6 plus 9 x7 equal to 0, x2 plus half x4 minus 12 x6 plus 3 x7 equal to 0, and x3 plus x6 equal to 1. And x1, x2, all variables are greater than equal to 0. So here x1, x2, x3 are the three variables that are the in basis, and x4, x5 and other variables, so x6, x7, they are in the non-basic variable. All right, because these x1, x2, x3 has values, and if you look at the values, the x1 is 0 and x2 equal to 0. That means the solution represented is your degenerate, isn't it? So you see what is happening: x1 equal to 0, x2 equal to 0, x3 equal to 1, and x1, x2, x3 forms the unity matrix. That is how the problem is in canonical form, and x4, x5, x6, x7 along with their this thing. So if the problem is one of minimization, so tell me which variable should be entering variable and which variable should be leaving variable. All right, so in this particular problem, it's seen that cycling occurs. The seventh table repeats the first table, and there is degeneracy because there are zeros in the basis in all the tables. In fact, these all the tables that you get subsequently, there will be zeros. That means already there is degeneracy. Now, you see it's a minimization problem. So the most negative value, that means x4 has the most negative Cj minus Zj. So x4 should be entering. And which variable should be leaving? There is a tie between x1 and x2. Isn't it? One of them has to leave. So exactly this is what is seen, that x4 is the entering variable, which is the leaving variable x1 and x2, and tie in the leaving variable between x1 and x2. There is a tie because both are 0. So 0 by anything becomes 0. So this is the example from VL. We are not solving it further, but one thing is clear, that next table is also going to be degenerate. And if you are not careful, like you are not using the Bland's rule, then you might be getting what is known as cycling. Order and variables in some, order the variable in some sequence, that is x1, x2, x3 to xn. Of all the non-basic variables to enter the basis, choose the one with the smallest index, that means leftmost. Of all the candidate to leave the basis, when there is a tie, choose the one with the smallest index, right? So that is that if you look at the variables, then one that is having a smaller index, that means x1 and x2, x1 has a smaller index. So always choose x1 if there is a tie between x1 and x2. So that is Bland's rule, very simple rule. And how does it break cycling? Because we are always choosing a variable in a pattern. In order to come back to the same table, we have to break that pattern, because if you keep doing a pattern that is always leftmost, then chances of getting back to the same pattern is not possible. Is all right. But if you are choosing variables randomly, then say for example there is a choice between x1, x2, x3. So, you are choosing say first x3 and then x1, then x2, then you cannot come back to x3 again if you follow Bland's rule, because you see Bland's rule will choose either x1 or x2 or some other variable. Is it all right? So that is how, unless you break the pattern, you cannot come back to the same table. So cycling could be broken by simply following a rule such as Bland's rule, which says that choose the leftmost variable or choose the variable with the smallest index. All right. So this is how the Bland's rule work. All right, so now there is a very important concept also, that so far we have seen that degeneracy occurs at the optimal point, but degeneracy can also occur at a temporary or in an non-optimal point also. So in that case, because the degeneracy has not occurred in the optimal point, so if you follow the right path, you can move over from the non-optimal point, which is a degenerate point or an intermediate point, to the optimal point where there is no degeneracy. Right, so it is not always that degeneracy has to occur at the optimal point. Degeneracy can also occur in a non-optimal point, which is called an intermediate point. The problem can therefore recover from the degeneracy thereafter. But what may happen, there could be cycling, which has to be broken by using the Bland's rule, or there will be additional number of iterations, which will make the simplex problem more difficult. So here is the problem. Maximize z equal to 3x1 plus 2x2 subject to 4x1 plus 3x2 less than equal to 12, and 4x1 plus x2 less than equal to 8, and 4x1 minus x2 also less than equal to 8, and x1 x2 greater than equal to 0. So if you draw this graphically, so you can see that this is the constraint, that is 4x1 plus 3x2 less than equal to 12. That is this line between A04 to this point. This point is not mentioned, but nevertheless, between A, B, if you extend that line where B is 3 by 2 by 2, then that is the 4x1 plus 3x2 less than equal to 12. You can solve also. This is 3, 0. So this point is 3, 0. So 4, 0, 4 to 3, 0, that line is 4x1 plus 3x2 less than equal to 12. Then there are two more lines. One is 4x1 plus x2 less than equal to 8. That is this line, right? 4x1 plus x2 less than equal to 8. So this goes from 0, 8 to 2, 0. Right? This point is 0, 8. This point is 2, 0. So this line is basically 4x1 plus x2 less than equal to 8. And this line, that is 4x1 minus x2 less than equal to 8. All right. So how many points are merged at C? See, there are three constant line. One is the axis. One is this constant line, that is 4x1 plus x2 equal to 8. And this constant line, that is 4x1 minus x2 equal to 8, that have merged. So basically there are 3 points that has merged, C1, C2, C3. It is possible that you keep moving from one to the other. But anyhow, since two constants are merged and two constants are satisfied simultaneously, there will be zero value in the basis and there will be degeneracy. However, C is not the optimal point because the value is less compared to some other point. So this is not a permanent degeneracy. This is a temporary degeneracy. All right. Note that B is the optimal point, right? So if we put this value, then objective function is the maximum. Now 3 points are merged at C. Therefore we have a temporary degeneracy there. Is it all right? So point C has a temporary degeneracy and not a permanent degeneracy. So here is the simplex first table. Maximize. So this is how by adding 3 variables, x3, x4, x5, we make it what you call as equality. in the augmented problem. So x3, x4, x5 are in the basis. Values are 12, 8, 8. x3, x4, x5 forms the unity matrix. The x1 and x2 are in the non-basic variable initially. So these are their coefficients. And since 3, 2 are the Cj values and Ci's are all zeros, so Zj equal to 0. So Cj minus Zj is 3 and 2. So which variable enters the basis? X1, because it has maximum Cj minus Zj in a maximization problem. So X1 enters the basis and there is a tie. Can you see there is a tie between X4 and X5? All right. So here x3 12 by 4 3, 8 by 4 2 and 8 by 4 2. So which one should be chosen? The by Bland's rule we should choose x4. Is it all right? So then you see that since both the resources are simultaneously exhausted, what is going to happen? One of them will come into the basis, right? That will remain in the basis. So if x4 leaves, then x5 remains in the basis, x1 comes into the basis, and the other variable, that means x5, would then assume a zero value. Is it all right? So this problem we are not solved, and we leave it at that. We know that there is going to be a temporary degeneracy, and that temporary degeneracy would lead to a zero value in the basis, although it is not going to be optimal point. So what may happen between C1, C2, C3, we might iterate 2-3 times or 1 or 2 times, and thereafter, if we are in the right path, then we can go to the optimal point. All right, so this is how the degeneracy is handled, particularly in case of temporary degeneracy. Now here is another LP problem. So quickly we can see, because we have discussed this problem earlier, but not in the context of degeneracy. So maximize Z equal to 28x1 plus 30x2 and subject to 6x1 plus 3x2 less than equal to 18 and 3x1 plus x2 less than equal to 8, 4x1 plus 5x2 less than equal to 30, and x1 greater than equal to 0 and x2 greater than equal to 0. So we add 3 more variables, they are slack variables, to get the augmented problem. So here is the augmented problem, and we write the first table. When we write the first table, one thing we find out that x3 18, the x4 8, x5 30, that is the initial solution. And x1 and x2, their profit coefficients are 28 and 30. Since 30 is higher in the Cj minus Zj, so x2 enters the basis. So which one should leave the basis? Look, x3 18 by 3 6, x4 8 by 1 8, x5 30 by 5 6. Can you see that there is again a tie? There is a tie in the leaving variable. Both x3 and x5 are candidates. So we have to choose one. The Bland's rule says that choose the lowest. That means choose the variable with the lowest possible coefficient, index value. So index is 3. Here it is 5. So x3 is our choice of the leaving variable. So when we do that and we go to the next table, what we find is that from the key row, we get the 6 to 1, 1 by 3, because everything is divided by 3, and 0 0. The key column has to be transformed to 1 0 0, and canonical form is obtained by x2 x4 x5. So 1 0 0 0 1 0 0 0 1, and the coefficients for x1 and x3 are now computed, and then we find that Cj minus Zj's are both negative. That means the optimal solution is obtained. So what is the optimum solution? x2 equal to 6, x4 equal to 2, and x5 equal to 0. All right, so that is the optimum solution. It is a degenerate solution because there is a 0 in the basis. So what is the final optimal solution? Because x1 and x2 are our final variables. So x1 equal to 0 and x2 equal to 6 and z equal to 180. Now a very interesting and important point we must mention here. You see, we are saying that this is the optimum table and this is the final optimum solution. Now look, the final optimum solution has a 0. You see, you will be tempted to say that since in the final optimal solution there is a 0, that is x1 star equal to 0, that means the problem is degenerate. This is a wrong answer. This is not correct at all. Look here, in the final table, x1 is not in the basis. x1 is in the non-basis. x2, x4 and x5 are in the basis. Is it all right? Although x1 is our major variable, because the original problem was expressed in terms of x1 and x2, and we are interested in the solution of x1 and x2 only. Let's go back to the problem once again. So this is our original linear programming problem. We need a solution to this problem. The variables are x1 and x2. We added some slack variables to solve the problem, but we are really not so much interested in the slack variable values. We are really interested in the x1, x2 values. And when we got the final optimal solution, we found that x1 and x2 are the solution in the original problem, and there is a 0 in x1. So if you just tempt to say that, you become tempted to say that, look, this is the degenerate solution I have got, you are then wrong, because x1 is equal to 0, not because it is in the basis. It has become 0 because it is not in the basis in the final table. So non-basic variable will be anyway having a 0 value. So these does not indicate that the final table is degenerate. The final table is degenerate because x5, one of the slack variable, have assumed a 0 value. Is it all right? So this is actually the optimum solution from the basis that x2 equal to 6, x4 equal to 2 and x5 equal to 0. All right. So because of that, this particular final table is degenerate. Now, since we are interested in x1 and x2 values, and since only x2 values are returned, so we know that x1 equal to 0 because it is not in the basis. So this fine difference must be very clearly understood so that we do not fall prey to the wrong interpretation. All right. Suppose, in the very first table, when there was a tie between x3 and x5, uh, if we would have chosen x5 rather than x3, what would have happened? Right? See, we do not get the optimal solution in the second table with x5 leaving. Very interesting. If we chosen x3, we get the optimal solution at one go. If we choose x5, then we do not. Now somebody may be thinking, no, you have applied Bland's rule, so we got better result. But that is not correct. Bland's rule only avoids cycling. It so happened that points are such that we need more iteration with x5 and less iteration with x3. Tomorrow in another problem, we might find if you choose, you have more iterations, and x5 you choose, then you have less iterations. So it is based on the values and based on how the constant lines are, and it has nothing to do with Bland's rule. Bland's rule only avoids cycling and nothing else. So do not think that because we are using Bland's rule, so we are avoiding excess number of iterations. All right, so it's not connected. All right, so once we understand that, if we choose x5, then this is the key row, and x2 again enters the basis. So x2 enters the basis, x5 leaves, and x3 becomes 0 then. So because of that, we say that this is a degenerate table, but this is not optimal, because if you compute, then with the intersecting element 5, we divide each element by 5, and then we get the key row. We also get the key column at 0, 0, 1, so that the canonical form can be maintained by the variables in the basis in that order, that is x3, x4, x2, and x1 and x2 coefficients are computed back again. All right, and after that, when you compute the Cj minus Zj, we find that for x1 it is positive, and for x5 it is negative. So x1 comes into the basis. So what happened? X1 uh, again will be now entering the basis. So which one should be leaving? Let us see that. So x1 is coming into the basis. So obviously x3 has to leave, because after all there is a 0. So what happened? X1 comes into the basis but with a 0 value. Is it all right? So x1 comes into the basis with a 0 value. And again, when we compute the final table actually looks like this. That is x1 equal to 0, x4 equal to 2, and x2 equal to 6. Right? This is a degenerate table because one of the variable in the basis x1 is at 0 value. So same optimal solution is obtained in the third table. The optimal solution is degenerate because there is a 0 value in the basis, and optimum solution is x1 equal to 0, x4 equal to 2, and x2 equal to 6, and z equal to 180. And then final optimal solution can be worked out. One very interesting thing you see, that x1 was not in the basis in the other optimum solution. Whereas in this optimum solution, when we are choosing x5 to leave the basis, that time x1 comes into the basis. Alright, so you might get, because essentially, although it is the same point, but the interpretation is not same, because 3 points have merged, we are getting different points when we are choosing x5 to leave, and when we chose x3 to leave, we got a different point. So different points are obtained, and therefore different optimal solutions are coming out, although it is the same point, because those points are merged. So these are the issues about degeneracy of a problem. And thank you very much for patiently hearing. What we shall do, the other kind of different other special cases we shall be discussing in our next class. Is it all right?